Okay, so if we were in class on a Friday morning, I would have said, let's be done with the worksheet. I have 3 important corollaries of the mean value theorem to talk about. These are corollaries of the mean value theorem. Corollaries are things that are true immediately as a result of some big idea. They're smaller theorems that fall directly from a bigger idea. Each of these ideas is important, and so we will prove each of them together. This is what we would have done in class in the last 15-20 minutes of our class time if we were together. We are not together, and so this is as close as we can come virtually. So here's corollary 1. Let f be differentiable on some interval I for interval. If f prime of x is 0 for all x on the interval, then f of x is k for some real number k. Let's be clear about what this says. This says that if your derivative is 0, you have to be some horizontal function, some function whose graph is a horizontal line. And you're thinking, wait a minute, we knew that already. No, you knew that if you were a horizontal line, then your derivative was 0. This logic goes the other way. This logic says if the derivative is 0, the only way that can happen is for the function to be a constant function. So we will prove this because we can. How do we go about proving this? So we pick any 2 numbers a and b in the interval. Let a be less than b. Let's just assume that a is less than b. Let's assume that f of a is not f of b. Let's give that a go. So what we'll do here is we'll assume that f of a is not f of b. Something's going to go tragically wrong in here, and we're going to say, where did we go wrong? Where did we go wrong? Where did we go? That's where we went wrong. And so it must be that f of a is f of b. So what does the mean value theorem tell us? If a is less than b, and if f of a is not f of b, then there has to be some place in between a and b where this quantity is not 0, because f of a is not f of b. So this numerator is not 0. But that's a problem because f prime is 0 everywhere on the interval. So if f prime is 0 everywhere on the interval, it's 0 everywhere between a and b. This is a contradiction. In other words, this can't happen. And because this can't happen, where did we go wrong? We went wrong here. Therefore, f of a equals f of b for all a and b on the interval. And if f of a is always equal to f of b, then the function is a constant, and we're done. So that's kind of a big deal. That tells us if the derivative is 0, then the function has to be some sort of constant function. there's a second corollary. And the second corollary says if f and g are differentiable on some interval I, and if f of x if f prime of x equals g prime of x on that interval, then f of x is g of x plus a constant for some constant c. So what does that even mean? What does that even mean? You already know that if you have some function f, and then just to make this extraordinarily realistic, you have some other function there, and let's just change it up, and let's change that up. That's great. So great. So this function will be f, and this function will be g. You already know that if two functions are the same except for a constant, then their derivatives have to match because the derivatives don't depend on vertical shift. This corollary takes the logic the other way. If you know that the two derivatives match, the only way that that can happen is for the functions to be the same except for a vertical shift. That's what this is going after. So we will prove this. We will let h be f minus g. If that's the case, then the derivative of h is the derivative of f minus the derivative of g. And what do we know about that? Well, if f prime is equal to g prime, that's 0 for all x. But wait a minute, if h prime is 0, by corollary 1, h is some constant. So f of x is g of x plus that constant. And this guarantees that the logic goes the other way. If the derivatives of two functions are equal, then those two functions are the same except for some vertical shift. The third corollary is by far the most important one, and it says, let f be continuous on some closed interval and differentiable on an open interval. And all that means is that the function is smooth everywhere except maybe at the endpoints. Maybe there's a corner at an endpoint, maybe there's a cusp at an endpoint, maybe there's a vertical tan or an asymptote at the endpoint. Does not matter. The function is going to be continuous on the closed interval, differentiable on the open interval. If f prime of x is positive on the open interval AB, then f is increasing on AB. And if f prime of x is negative on AB, then f is decreasing on AB. So here's the rough way we go at this. There's going to be stuff that I'm going to write and then stuff that I'm going to say but not write. So you're going to have to, when you make this into your notes, you're going to have to decide how you want to write this thing down. This is a sketch of how the proof goes. We're going to pick A and B with A less than B. And we're going to consider f prime of C, which by the mean value theorem is f of B minus f of A over B minus A for some C that's in between A and B. So there's some C between A and B for which this is true. Okay? So let's consider this case first. What if f prime is positive between A and B? Well, that means that this number is positive. And we know that A is less than B, so this number is positive, which means that this number must be positive. And that must happen because a positive divided by a positive is a positive, but a negative divided by a positive is not a positive. So this number has to be positive. And if this number has to be positive, then f of b has to be bigger than f of a, which means the y value on the right has to be higher than the y value on the left, which means that the function is increasing. And there's a similar argument to take if f prime is negative. If f prime is negative, but this is still positive, then this has to be negative, and that means the y value on the right is lower than the y value on the left, which means that our function has to be decreasing. So how you choose to write all that out is up to you, but that is the basic idea. We take a look at middle school signs of integers, and we apply that in this case. Those are three things that I would have on index cards committed to memory. If I were you, we're going to need them as time goes on. All right, you are now capable of answering the other three questions on that worksheet. I am not going to post a video with my answers to that, so I'm hoping that you will come up with those on your own. All right, week 1 in the books. All the best to you. See you soon.